This section is all about getting you ready for the coordinate proofs that happen next section. I know you're excited. To prepare you for these proofs, you need to get used to generalized coordinates. Up until now, you have mostly dealt with definite coordinates. In this picture here, we know the vertices of our triangle are at -3, 6, -5, -3, and 5, -4. We know the exact numbers of the coordinates. However, we are now going to transition to generalized coordinates, where we don't know the exact numbers. Now we have a square, but there are no more labels. The grid is completely gone. We just have our axes and a square plopped down in the middle of it. We are told that this square is centered at the origin with a side length of 2a, and that we are to label the 4 vertices of our square. Obviously, we can't use any actual numbers here. We need to generalize. Since our square has a side length of 2a, we know that these are the lengths of all the line segments that make up the square. Makes sense? Since we know these lengths are all of length a, how will that help us label all of our coordinates? Pause the video now to try it for yourself before I give you the answer. See if you can properly label them all. These are the coordinates of our vertices without using any numbers. They have been generalized. Let's try another one. Here I have a rectangle. The y-axis is splitting it right in half. The height of our rectangle is b, and the length is 2c. Given that, what are the lengths of our red line segments in the picture? These are the lengths. Pause here to make sure you understand where those lengths came from before going on. Now we need to label our vertices. What should they be? Are you going to pause here, or are you just going to let me show you the answer? These are the appropriate labels. Did you get them right? What do you think of these generalized coordinates? Now let's see how these generalized coordinates get used in our formulas. You are used to plugging in numbers into these equations. Let's see what happens if we plug variables in instead. Here I have a parallelogram where I have already labeled the vertices with generalized coordinates. Make sure you understand why the top right coordinate is 2d plus 2e for the x-coordinate. I will talk later about why there are 2's all over the place. For this problem, we need the midpoint formula. So I will get rid of the others for now. It doesn't matter which diagonal we use, we will get the same answer. Since one of our coordinates is 0, 0, that seems like a good pair to use. This is another good time to try it before I give you the answer. This is what you should have gotten for the midpoint. Make sure you can follow what happened. These are the coordinates of our point of intersection. Now why do you think this problem started out with 2's everywhere? It's common any time a midpoint formula is needed, since it naturally cancels out the division. Our final answer was a nice whole variable without fractions. It certainly would have worked out without all of the 2's at the start, but our final answer would have been divided by 2. It's a pretty big hint that if you see generalized coordinates with a 2 in them, that you will be using the midpoint formula at some point. This has all been laying the groundwork for you to be able to do a coordinate proof. A coordinate proof is a proof that uses coordinate geometry and algebra to prove geometric theorems. This book doesn't specifically cover it, but there is a theorem in geometry that says the midpoint of the hypotenuse of a right triangle is equidistant from the 3 vertices. You can prove this using a coordinate proof. Let's come up with a plan to set up the basics to see what it looks like. We won't actually do it out fully. That's for the next section. All we are doing here is planning it out. First, just like most geometry proofs, there is usually a picture. This picture has generalized the coordinates, and look at those 2's there. That must mean the midpoint formula is coming. Next we have a given and a prove, just like our other proofs. Turning this theorem into a given and a prove gives us the. If we can show that AB equals BM equals MC, then we will have proven our theorem. From here, we don't put up 2 columns. We sort of talk through the proof with math in between. It looks more like a paragraph proof than a 2-column proof, but coordinate proofs tend to have a lot more math than paragraph proofs. Here we are just coming up with a plan. Our first step in our plan is we need to use the midpoint formula to find the coordinates of M. If we were doing the full proof, we would then put the math right after that line, calculating the midpoint formula with all of these coordinates in. Once we find out what M is, then we can use that with the distance formula to calculate the values of AM, BM, and MC. If our theorem is correct, they should all show the same value. Once again, if we were going to do the full proof, we would actually show the full calculations at this time. All 3 distance formula calculations need to be shown. That's the basics of generalizing coordinates and planning out a coordinate proof. I know you're looking forward to next section when you need to do out a full coordinate proof.